person IIA Colloquium in a long time. And it's my pleasure to welcome Dr. Madhulika Guhathakurta, fondly known as Lika to most of us. She is the Senior Advisor for New Initiatives, Heliophysics Division, NASA, and she's a Program Scientist at GSFC, NASA headquarters. For the past two decades, Dr. Guhathakurta has enabled the development of heliophysics as an integrated scientific discipline from which fundamental discoveries of our universe provide direct benefits to the society. She was the lead of the Living with the Star program for 16 years since its inception in the year 2000. And a lot of us solar physicists have benefited from this program through different. In fact, I first met Lika in a Living with the Star program in Goa a long time ago. So then she made possible the flagship missions, the NASA flagship missions like the Solar Dynamics Observatory, the Van Allen probes, Solar Orbiter collaboration with the ESA, as well as the Parker Solar Probe. And of course, there are many other missions, including STEREO, that would revolutionize our understanding of how sun affects the heliospheric space weather. To accelerate innovation and scientific discovery, she created funding mechanisms to shepherd traditional domain scientists out of their comfort zones. That's a very huge task. To create the LWS system science, known as the Targeted Research and Technology Program, and focus science teams that foster competitive yet collaborative environments that promote cross-pollination of science ideas and technology. To nurture the next generation of leaders in heliophysics, she created the Jack Eddy Fellowship Program, the postdoctoral program, which has become an important channel for professional growth of promising researchers. Since 2017, she has championed the growth of the Frontier Development Lab, or the FDL, both in terms of the breadth of the problem areas tackled as well as the number of agency and industry partners. The type of innovative solutions include virtual telescopes, data fusion, edge computing, autonomy, and this approach will have an enduring imprint on the way science exploration is carried out by future generations. Presently, she is back at the NASA headquarters where she is a program scientist and also splitting her time as a senior advisor for new initiatives at the Heliophysics division at GSFC. So with this, I would invite Dr. Madhulika Guhathakurta to please give her talk on applied artificial intelligence for science exploration enabled by public-private partnerships. Thank you.
Thank you. Thank you so much, Yali, for that really wonderful summarization of my work. I think I can stand here and say that I have spent one magnetic solar cycle, really 22 years, in a very bureaucratic world of NASA headquarters. So Goddard Space Flight Center is the research wing of heliophysics. That's where scientists practice science, but headquarters is where policy is developed, missions are created, and the kind of science research we are going to support happens. And I think heliophysics sort of came into existence during this time frame. Heliophysics wasn't always heliophysics because it is not just solar physics. It is actually the impact of the sun on our planet, on other planets, in the interplanetary medium, to the very edge of the interstellar medium where the Voyager spacecrafts are. So what I wanted to do, instead of kind of talking to you about programmatic stuff, I really want to tell you sort of the next chapter that has become my life in the previous few years, while at headquarters, I took something like a sabbatical and went to one of the other NASA centers, which is NASA Ames Research Center, which is another innovation center because it is in the heart of the Silicon Valley. And I kind of wanted to see, how can we be entrepreneurial in science and bring the private side and all of that. But I absolutely had no idea where I was going to get to while I went there. I mean, I went with ideas, but you never know how it's going to shape. And so, it became sort of my brave new world. The novel written by Aldous Huxley, the English writer back in 1931. Now, the concept of, and many of you young people probably haven't read that. We used to read those books when we were young. Brave New World describes a dystopian world, but, after coming in contact with what's possible with artificial intelligence, it's for me, it's no longer that negative utopia, but as referred to in that book. But my vision is that it will lead us into the real utopian world that we see, provided we use our technology the right way. And of course, machine learning is becoming basically a very important tool for science. NASA's Heliophysics division, what it has done in the last 5 years is basically jumped into it by pushing the limits of what AI/ML can do through its partnership with the Frontier Development Lab to better understand our star, predict its interaction with Earth. And by virtue of that understanding, we are enabling sun-planet connections, star and exoplanet connection, because the basic physics is still the basic physics. So this talk will be a general overview of what's possible when ML is applied to science domains with massive heterogeneous data that we have, helping both to sort of safeguard and improve life on Earth. These are our sort of core goals, principles in heliophysics. Unlock the secrets of the universe, which we are going to do through JWST, and better understand habitability in the larger context of exoplanet. And I'll showcase some cutting-edge applications of machine learning to the physical sciences through the lens of heliophysics mostly. I'll provide some examples of earth science, astrophysics, planetary science, and show you AI/ML's sort of power as a tool for exploration and discovery. So that's a long start. It's a play. So this is a movie from Solar Dynamics Observatory. I think many of you probably know a lot more about the data, the science, because I don't get to do science. I create these mechanisms for all of you to really get the science out of. So basically, sun's fiery nature, along with its tremendous gravitational pull and extensive magnetic field, help it to become the heart of the solar system. When the people don't kind of always acknowledge JWST becomes more important than heliophysics, and there are always tensions across adjacent disciplines like heliophysics, astrophysics, right? So magnetism describes virtually every, let's see if I can continue to play this. It plays a very important role on the sun, from the sunspots to the soaring prominences to the spicules that Piali's group just recently published. Everything is driven by magnetism. So heliophysics basically has three forces. That's the mechanism of how heliophysics operates and their interactions. So pressure, gravity, and magnetic field. And magnetic field being the most dominant. What's the difference between heliophysics, space weather, and terrestrial Earth weather? It's really magnetic field. Magnetic field makes everything immensely more complicated. Heliophysics is an environmental science. It's a hybrid between astrophysics, sun as a star, and meteorology. When you look at the space weather component of how sun's variability, radiation, particles, magnetic field impacts aeronomy, ionosphere, magnetosphere. So those are geospace environment, which is where the space weather impact is felt. Technology is affected. Solar wind interacts with Earth's magnetic field, creating this energization process, right? And so processes operating at one scale basically has influence on other system. And it is a very, so I've kind of drawn a cartoon description there. It's a very complex system with many different temporal and spatial scales, right? And the system is multi-scale and couples between scales. And to give you examples, the heliophysics system is, typically kind of has more than 20 orders of magnitude that separates the largest and smallest scales of interest. Just think about that. That's what we are dealing with. And we have to reproduce that through our physics understanding and through our simulations. And for those simulations, you absolutely need massive amount of computer. So these are kind of also our requirements to describe our system. This particular picture is basically solar wind impinging on Earth's radiation belt. So it's a simulation model, and you can see the shape of the magnetosphere. It's quivering like a cocoon from the variation of the solar wind pressure and radiation. But that's what also keeps us safe and keeps the harmful radiations away. This is the societal impacts of solar variability. It's very basic, human radiation, the radiation generated from solar energetic particles, galactic cosmic rays can affect human health in deep space, even in space station. Its impact on technology, anything that has electronic on-off switch has the potential to be affected by space weather. And our societies are getting very much dependent on technology. Your cell phone, operates on what? Satellite communications. If the satellite malfunction because there was a solar storm, then basically you don't have cell phone reception, internet, power grid. You can go on, and this kind of dependence of what's happening on the sun and what is happening to our technology is ever growing. I mean, we are learning. Think about autonomous cars, right? We didn't imagine this like 10 years ago. Autonomous cars, the same thing. We are simulating by taking a lot of satellite images, creating an environment in which a car can function on its own. Again, technology, those satellite data are not available. Of course, there's redundancy, but for how long? Then we become very vulnerable. So, and then there are new technologies, new ideas being generated, every day. So I would say it is what we still don't know. And of course, terrestrial climate. Terrestrial climate, both short and long term, is dependent on what the sun is doing. Now, normally what we do is we take total solar irradiance, the full radiation of the sun, use it almost like a black box approach as an input to climate model. But spectral irradiance, as we are finding, is very interesting, which is showing, tantalizing evidence of regional variability, which becomes very important because we live on different parts of the planet. So whether the global temperature in the ocean is going up by certain degrees, it's hard to compute intuitively. But if you live in Bangalore or Mumbai or Kolkata, what's the monsoon going to do? Is there a regional component to that? What's the drought going to do? It's important for the farmers, and it's all across. So these are things we haven't really tackled yet, and we must. that's kind of, sort of the societal benefit component of it. You're doing really cutting edge science because we haven't done it before, but it also has relevance to life and society. So this just kind of captures that it's not just our planet, it's the entire solar system that lives with the star. These are images from some of our operating missions. You're looking at SOHO-LASPO images. On the bottom, you're seeing stereo capture of CMEs. And on the left-hand side there, you see little letters written Earth. So we have now been able to capture the solar wind in images, which was unthinkable before stereo launched and gave us this perspective. So every planet, every object in the solar system is basically susceptible to the same forces from the sun. And this is kind of a fun example, a planetary magnetic field makes a difference. How is that? So we have a very robust magnetic field. So for planets like Mars, what we found that the consequences can be severe. Some, less than 1 billion years ago, Mars had a pretty robust global magnetic field, but that kind of ceased to be. We don't know why, removing the planet's main protection from the solar wind. So as measured on the top of Mars's atmosphere, essentially, the solar wind, which is kind of moving, average speed, moving particles that are mostly protons, hits on the surface of the planet and at about a million miles per hour, which is about 0.15% of the speed of light, significantly fast. And these particles then collide with the wind and they get energized and they are removed, right? So Mars is actually, they escape Mars's gravity. Mars is losing about 100 grams, a quarter of a pound of atmosphere every second. Now, the rate of atmospheric loss goes up by a factor of 10 or 20 when there is a big solar storm. And we call that, a Big Mac attack. Basically, the tribe being killed, essentially. But people understand better, if you eat a hamburger, a quarter pounder, how much mass is the planet losing.
This would be the same scenario for Venus also. It doesn't have a magnetic field. It's nearby, and it has a thick atmosphere.
Absolutely. These are all. So, one thing that I don't talk about here, but since you're bringing it up, but I'm giving you the description of it. The first textbooks of heliophysics as an integrated science was created under my leadership by different people. I didn't write the books. There are 3 textbooks on heliophysics. If you go to the UCAR Heliophysics Summer School website, you'll find them. The 4th book was created just a few years ago called Comparative Heliophysics. That's where you're going to see the description of, how heliophysics knowledge and it gives us the interaction of these heliophysics forces with different planets. It could be just Aeronomy, or it could be like Jupiter, with huge magnetic field with its own auroral system. So there's like a give and take. We learn from these systems and we utilize our knowledge of our sun-earth system and take it elsewhere. So what this is showing is really because the interest in exoplanet has grown exponentially in the last several years. And we've kind of always defined habitable zone to be the region where liquid water can exist on the planetary surface. That was kind of the beginning of exoplanet world till heliophysicists got into the business and started showing that, after all, we are doing parameter space study. So think about, numerically red dwarfs are make up to 80% of the stars in the Milky Way, right? And so the question became, does extreme space weather render these systems lifeless? So you're seeing one such example. Not only is the habitable zone of dim red dwarf much closer to the star in this particular case than our own solar system's habitable zone. But the rapid spin, deep convective zones of red dwarfs can supercharge basically space weather. And so some red dwarfs are spots that cover over 50% of the stellar disk. I mean, that's real. Those are things we are measuring, but now we are actually creating models out of that. So in fact, studies are showing that this can strip off the weather system, the atmosphere from the planet. So then what is a habitable zone? If the habitable zone is where we can live, then, and we have taken away essentially the atmosphere because of this interaction between star and planet, the concept of habitable zone has now changed. It's no longer just finding liquid water, it's just only one component. So question became, what is NASA doing with all this data? You know, we take about 2 gigabytes of data every 15 seconds from over 100 operating spacecraft. Now, to that, we can add all the ground-based observatories, we can add all the observations that are taken by many other agencies in the world, and the newer ones that are coming up. And, you know, data is the collection rate right now with JWST launching is growing absolutely exponentially, and handling, sorting, and managing this data is a massive challenge for us. So our data is one of our, I would say, and it should be for all of us, valuable assets, and its strategic importance in our research and science is huge, huge. And that's where AI/ML essentially comes in. So we as NASA are committed to making our data as accessible and as possible for the benefit of our work for the humankind, you know, basically through the innovation and creativity of the over 7 billion people on this planet who don't work for NASA. That's all of you. And then, you know, one of my goals is to create, you know, stronger, more robust kind of partnership and collaborative ideas so that we utilize all of our data together as a planet, at least for heliophysics, you know, of which I'm part of. So this is, I'm going to give you very quickly like a 101 of, you know, why AI/ML has become important. And normally in any audience, I would say there are a few who are just getting their head into AI, and sometimes it's kind of nice to have it explained by someone like me, who is more right-brained and knows just enough to get by. So don't ask me very difficult questions, you know, follow on to the talk about AI/ML. I just know enough to kind of figure out what areas to push. But the point here is that we can now digitize anything we want. It could be a cat, a face, a DNA, scent of a flower. Just imagine that. And once it's mapped and we have labeled examples, we can train a neural net. That's the fundamental premise, you know. Demystify AI/ML. AI is nothing but, you know, sophisticated mathematical tools based on tensor analysis, and we continuously, but it's all math. It's all math, you know. Aspects of it are statistics, you know, PDEs, things that you deal with. So we can spend the time and figure out what it is actually doing. Most of the time we haven't, but explainable AI is becoming very important. So this is kind of the digitization part of it, right? You can digitize something. And this is what we are trying to do, is we are going to show a simple example, something we did in the very first year of the Frontier Development Lab, is we put actually meteorite in a field, a real one, and then rocks all around, and say, can tool inference model really distinguish between this? So that's kind of the demonstration I'm trying to give you. And so this is what you are seeing. So in this case, we are training a neural net to recognize meteorites. Meteorites generally look a little different from rocks as they haven't been softened by erosion. So there is like a black fusion crust. So you have to have some recognizable, observable parameters. And after about sort of 26,000 images of meteorites, the neural net was able to recognize, it got trained, and it becomes an inference model or learner. And a learner you could call as a probability matrix, right? So again, it demystifies what we think AI to be, right? That it's a black box. It's not a black box. And so after we have generated this inference model, we let it loose actually in the real world. And that's where we have placed a real meteorite with lots of rods, right? And this is a meteorite drone that you're looking at. And the meteorite drone is looking for pristine meteorite faults. Before they oxidize and all that, you should have that black fusion crust on top. And what we found from this, after studying this, is that the result was pretty incredible. This inference model was very successful. It found 16,000 possibles, but also the actual meteorite with only 2 false positives. This is very, very important in real life when you're doing actual prediction, maybe fire, maybe flood, to get kind of to reduce, the false positives, because those become costly then, because people have to take steps when you have false positives. In this case, of course, we are just testing the system, how it works. And this is my last movie, and the 101 is essentially AI/ML. So you can train a neural net, as you saw, to learn to recognize sort of a digitized thing with a high degree of probability. But where it gets interesting is, when you don't have the training data set, that's very important. You have to have that. And when you're working with 3D multidimensional heterogeneous data, and that it becomes very complicated, right? So that's why this GIF is very illustrative. And if you look at it, once an inference model is trained, you can see patterns, which you couldn't without it. If I asked you to pull the pattern sitting down here, you wouldn't be able to see it. But an inference model is actually picking it out. And the reason we can't do this is simply the limitations of our mammalian senses. So again, I would say, when people become defensive about AI and calling it a black box, I like to think of AI as not artificial intelligence, nothing artificial about it, maybe. It's augmented intelligence. If I take off, this is augmented vision. If I take off my glasses, I don't see all as well. Hearing, telescopes, microscopes, they are the ones that are giving us the knowledge of the universe, but we don't think of them as artificial, right? We call this artificial. So think of it as augmented intelligence that is adding to our knowledge that we don't have any other way of accessing. So this is very quickly, space science is data heavy. As you can see, the blue line is the deep learning curve. And so deep learning is something that's still performing and its performance rate is not decreasing. So if you give the system more data, it does better with accuracy, prediction, forecast, whatever you're looking for. While the traditional methods in red are actually plateauing. So that's another powerful thing about what deep learning is actually teaching us, or how we can use it still, because we can, data is something we have, which goes underutilized, especially from big missions. So what happens when AI meets science, deep learning meets deep science with public-private partnership, because they are the ones who have generated these big inference models, which takes billions of dollars to create. So no space agency is going to do that, but utilizing, leveraging becomes very important. The partnership of public-private partnership in that regard. And I'd say that there are new discoveries in science that come about. And so these are kind of different areas. And this is sort of focused on what NASA has done, but this is sort of ubiquitous. You can apply it anywhere in any science, and not just science, human resources. I mean, the application of AI is pretty mind-boggling to me if you use it right. So the players here are the Frontier Development Club, very briefly what it is. These are kind of early career PhDs in AI/ML, computer science, early career PhDs in space research, domain scientists, basically AI and deep learning computer scientists, subject matter experts, NASA stakeholders, other agency stakeholders, industry partners, academia. They come together over a period of 8 weeks in summer, where we define kind of challenging problems, that doesn't have an obvious answer in the academic world because we don't understand the physics, and let loose, like the meteorite drone, we let loose these young people's minds. So in 8 weeks, what they are coming up with, and I don't know if any of you participated in any of the ideas, but a lot of students from India actually do participate. It is quite amazing to see the final product. And of course, that is NVIDIA building in Silicon Valley, and partnership with these private sector is important to get access to their GPU, to get access to the experience of the people there, to get access to their inference model. And in return, they are able to utilize, science data for something better, for betterment of humankind, but also actually learning and kind of making creating better versions of their already existing models. So any partnership has to be mutually beneficial to both sides. It's worked remarkably well. It's a small program. Someday it will be big, but it has demonstrated what is possible. These are something I'm keeping an eye on the clock. Don't want to go too much in detail about this, but this is kind of giving a few definitions of artificial intelligence. There are so many terms that is used. There is machine learning, there is data mining, there is deep learning. That's kind of what we do, correct? So machine learning is a branch of artificial intelligence. That's the overarching thing in which a computer progressively improves its performance on a specific task by learning from data without being explicitly programmed. That's kind of the underlying concept. And closely related to that are computational statistics, which focuses on prediction and optimization, data mining, which is kind of looking at discovering patterns in large data sets, which becomes very important in astrophysics, solar physics. Deep learning is probably the most active area of AI, which is, as I mentioned, exponentially growing. And it's an explicit extension of machine learning that uses mathematical concept of neural network to loosely simulate information processing and adaptation patterns seen in biological nervous system. That's kind of how it started. It does not require explicit tinkering by the domain scientists. It actually figures out kind of solutions over time and converts it. It's really fascinating. Also, there is exponential investment, patents, publications, funding, has fueled rapid advances in the development of deep learning capabilities to make predictions, to identify anomalies, and even create new content that mimics what has been previously seen. And I want to give you some examples of that. This is just another version of that. for ML, more data does not really provide better results. So I'm telling this to you as students, when you choose your problem, you have to kind of think about, is my question really appropriate for ML or AI? And if it is ML, is this something I must do with it? ML, or could I use like statistics we have used? So what we find anymore are people are interchanging these terminologies, and there are lots of proliferation of papers. Now, compute resources are very scarce. So we really posing the right question and making sure you have the right kind of data is absolutely important so that we don't, misuse the limited resources we have. So this is, since I am at Indian Institute of Astrophysics, I'll show you these are not examples that FDL created, but what you can see is that there are astrophysical systems, images. I don't know which mission this is, where you have taken so many images with noise, basically, that you can apply GAN type of tool to remove the noise. So on this side, what you're seeing is the noisy, degraded images. This is actually the cleaner images. Now imagine when you have these, the science questions you posed, you can find better verification for whatever science you did. Or here we have automatic discovery of dipoles on our own planet. These are all discovery. It's not just prediction. Here, what you're seeing, this is from ESA Gaia data, hypervelocity stars. So I'd say go back and look at some of these examples, what they have done, how to utilize some of these tools for the kind of questions you might ask in future or asking. And this just basically gives you, just separating it out, what is deep learning and what is machine learning. And these are terminologies that people use a lot. And again, deep learning is really sort of convolution neural network, deconvolution neural net, generative adversarial networks. ML has a lot of statistics included in it. But many of you actually utilize all this. I don't have to go through them, but these are some of the tools that are available, and you have to figure out what tools to use. And that's why partnership between domain experts and computer experts is critical to any problem you're trying to solve. Okay, so now what I'm going to do is quickly go into, my God, I'm running out of time. Okay. So this is the Heliophysics System Observatory that I talked about. We have about 20 plus operating spacecraft. So for heliophysics, this is where we get essentially all of the heterogeneous data that I was talking about. Show you the next image, and that will give you a sense of where are these particular observatories located in space. So they are, anywhere, and these are satellites from NASA and NOAA, and we use them a lot, not just for basic science, but also space weather prediction, which is becoming very important. And this visualizes the orbits, from very close to Earth in geospace environment to deep inside, Venus and Mercury, like Parker Solar Probe or Solar Orbiter going out of the ecliptic, this Mercury Messenger, Bepi-Colombo, all kinds of data, which is really revolutionizing our understanding of the inner solar system, because we haven't had so many observatories sort of focusing on what is happening to the sun, what is coming out. And with that, I want to share, I think, your team here with Piali, the recent paper on spicules is like amazing. That's innovation, creativity. You thought of someone saw something, right? Maybe water droplet on alligators meeting, or and utilizing that concept. You brought different kinds of interdisciplinary scientists and mathematicians to work on this and pose the question and take it to its conclusion. And when the conclusion kind of gets verified with observation, that's like a aha moment. That's really cool. So these are, for innovation, you don't have to have a big mission. There are already lots of data. How do you utilize data to pose your question and then answer that? This is what we are looking at in terms of data. And again, as I mentioned, this is heliophysics data. So we have something like 8.7 petabytes of data. It's a lot of data. I've given you sort of references, the data volume for Solar Dynamics Observatory. DIC is the ground-based NSF observatory. You can see how huge that's going to be when it has collected its data. Not quite sure how that's going to be tackled. In comparison, the in situ data, which are particle data, is just minuscule, but they are very important, and also very heterogeneous. So kind of creating that cross-calibrated platform becomes very important. But this is what we are dealing with. And again, I'd say add JWST to this, like where are we going? How are we going to deal with it? Not one single principal investigator or researcher can tackle science questions this way anymore. So this is kind of giving you an overview of what heliophysics has done over the past 5 years in integrating AI/ML into some of the science questions. We've kind of generated some 13 helio-ML related topics, 21 publications, and remember these are all done during 8 weeks of summer. And integration of physics, what's happening, things never remain static. So as we are evolving with our questions, we are integrating physics model and explainability is enabling AI to become a really powerful tool for discovery. That's where the science is moving. And so these are examples of problems we have solved. Maybe I might not get chance to go through all of them, but this is one is like super resolve. It's kind of creating a long-term magnetic field database that many of you in solar physics here would appreciate because India is taken as one of the longest database. Okay, so this is an example of workflow optimization, which is cost and time savings basically, and results in enhanced data products, 50 years of solar magnetic field data, or create virtual instruments on Solar Dynamics Observatory. One of the sensors on one of the telescopes stopped functioning in 2014. And the question was, can we take all the other data that are still operating and create essentially that missing gap? This is you have training data, and then you are able to reproduce the data. And the answer was amazing. The answer was better than what we were getting by using differential emission measure, which is physics-based model. We make forecasts, which is like applying decision intelligence with rapid assessment, improved strategic decisions. For example, GPS, GNSS, disruption 1 hour in advance, that saves lives. I mean, these are really, really important topics if we can really break into it and give really good prediction. Or I would say extract insight from noise is an example of anomaly detection, that is mapping star spots hidden in test data. You can pull that out. And we learn from that. We apply our science knowledge from sun as a star to an entirely different population of stars. Or auto-calibration. If you're flying a UV detector in space, it is going to degrade. And so we have to underfly rocket to calibrate those instruments often. That's what we do for STO. What if we could self-calibrate? And what we have figured out with all the filters that we add, all the data that we collect, we can do auto-calibration. So imagine the future of science mission can look very different, where it doesn't have to be all that heavy and have everything in one instrument, but you can have few filters and you can generate the other wavelength by synthetic processing of AI/ML and generate other spectral irradiance, which kind of disappeared on us. Its potential is really pretty untapped right now. So this is kind of quickly, I'm going to go over this. These are examples. So this is basically kind of trying to create a homogeneous set of magnetogram. As we talked about, this database, there is ground-based data, there is really high resolution noded data, which is from a very small region, but there is high resolution MDI data from SOHO, and there is even higher resolution HMI data from HMI from SDO. So the concept was bring all of this together and can we super resolve, let's say, GONG data to HMI level? And we can. This is again 2 weeks of work and you can begin to experiment. This is just showing the possibilities. These are not finished product, but showing the window is open. There's a lot we can do. This is, in fact, what you're seeing here is SOHO MDI ML input. This is the target region we were working on, and this is the ML output. So you can take GONG data and convert it into MDI resolution or HMI resolution. You can do that. The information content is there. It's fascinating. Questions we never asked before. My God, I have so many more slides. I'm not going to talk about all of this. This is an example of auto-calibrate from SDO data. So you can see how the instruments are degrading, right? And this is after auto-calibration, we have removed that. So normally we would underfly a rocket to get there, but you can actually do it with AI/ML and existing data. So the goal is that SDO has to continue to take data, and then we can have training tools and we can create algorithm that will ingest the new data being taken and provide us with this. So this is again kind of quickly giving you, what we can do with the data set we have created with IIA, all the filters, IIA ML data, and this is actually available online. And later when I talk with you guys, you students, I'll show you where you can access it. It's open access, and you can start fiddling with it, actually. That's the only way a system improves. Utilize it, write papers and see what else needs to be done. But everything that we have created on the AI/ML platform is available to you. And so these techniques basically enhance the scientific return of science mission and paves the way for an autonomous space weather constellation in the future, which would be perhaps lower in cost and power so that we can do it more efficiently simply because we will have some of these embedded tools. This is the one that I was talking to you about, by using AI-ready SDO data set. What we could do is use 4 years of 7 cotemporal UV channels from SDO IIA, and we were able to actually develop that sensor, which malfunctioned on extreme variability experiment. The sensor, MEGZE, that was giving us spectral irradiance input, which is most critical to ionosphere because that's what the ionosphere absorbs and essentially energizes. That's where all the technological malfunctions are happening. And now we have an algorithm that can do that. By the way, we have not kind of operationalized any of these. In order to operationalize any of these tools, we have to go through a process of verification and validation and all of that. But these are available, these have been published, so these are real things. So here you are seeing basically, the neural network strategy of creating the spectral irradiance data, the synthetic spectrum on that side. But once you have that synthetic spectrum, there are sort of corollary derivatives to that. So what you're seeing here is basically that energy input creates the ionosphere, creates thermospheric drag. So I'm sure you must have read very recently in February, Starlink launched several satellites, and so I forget, 49, 50 something. And this was during an active solar storm, but it wasn't a very powerful solar storm or anything, pretty ordinary looking CME. They lost 39 of those satellites. And that was because of the way the ionosphere got energized. So if we had real measurements there, we could have said that the thermospheric densities increased so much and there's going to be a significant thermospheric drag. These kind of tools are going to enable that. This is again, this is Parker Solar Probe, which is all the rage. I kid you not, I was less excited, even though this is a mission for which I think I stayed on at NASA headquarters to see it through. But the first 2 years, the data was okay. But what it is doing after crossing the Alpine boundary, the data we are seeing is mind-boggling. This will lead to new science. So one of the questions, this is with the earlier data taken by Parker, that we asked is, how do you really handle this massive amount of data? Again, people are doing just one event kind of analysis and you want to do much more than that, right? So question is, can AI help us find complex structures in the solar wind? The answer is absolutely yes. ML can learn to find, organize, and classify these complex structures. And what you're seeing there are some examples. So interplanetary CME, force detection, that's a complex structure in 1971. Interplanetary magnetic field enhancement in force detection, 1983. These were all associated with certain missions at that time. Switchback, the flipping of magnetic field, rapid flipping, even though we had seen it, but not with the kind of statistics we have seen. Force detection, 2019, from really Parker Solar Probe. And I put the question down, what next? That's going to come from the approach of these kind of tools. Next, this is something I think the astrophysicists here would like. So the question we asked is, what can we learn about heliophysics from stars? Telescopes like Kepler and TESS measure brightness over time, right, on single pixels for stars, starlights years away. So ML can basically learn from faint star observations to explain luminosity depths. That's what we see through competing plausible, hypotheses in terms of extrasolar transits, spot formation, whatever it might be, and the rotational characteristics of each star. And so we actually have created a pipeline starry spotter transforms Kepler light curves into images and stacks them and applies computer vision to extract star spots properties. Okay. I'm going to show you what I have, but I can see the time. I'm not going to go through this, but I just want you to be aware that these are the kind of things that AI and tools can do. And you can pose sophisticated questions and try to get answers, provided you have formed the right group, you have the right expertise, the right data calculated, and AI ready. So this is actually from Earth Science Division. Just for break, just take a look at this, what we are doing here. I'm not, the example I have here is essentially trying to predict flood. Flood is a devastating natural phenomenon where property damage, cost to human life is humongous, right? So if we can utilize all our satellite data to do prediction of flood, imagine how terrific that would be. So this is actually, this particular FDL topic actually took up that challenge and demonstrated that that's possible. And again, remember what I showed you in the very beginning, more data means more accuracy. So in 8 weeks, we kind of bring as much data as we can and show the proof of concept. But we can build gigantic predictive codes based on this. And then I don't think AIML is answer alone. As I was saying, we have to integrate the physics-based model into. So these are basically, this was a description. I'm not going to go over this, but the results, this is the result that you're seeing in terms of prediction. So what you're looking here is the predicted peak time, actual peak time, very close. So remember, I was talking to you about false positives, false negatives. These are all very important components when you are dealing with human lives. If you're giving out warning too often, that's not false negative, then people get used to it, and next time you give out real warning, nobody listens to you. Same thing, if you have actually, the opposite side of it is just as true. So these measures are very important when we are doing predictive diagnostic. This will be true for space weather forecasting for us, very much so, for which we have to depend on kind of the work that all of you are doing here, right? I mean, not just here, but all across the globe to get the right kind of input. Today, we don't know, for the model you have created for SPICUs, exactly how does that get folded into energizing the solar wind, or what happens during a sea propagation that kind of creates its own energization process. I mean, these are things that will be built over time, but that's kind of what we are trying to do. Returning back to the moon, we are going back to the moon with vengeance almost, it seems like, just a few years ago, we celebrated the first landing on moon, and now we are going to go back there and stay. And in order to go to moon and build infrastructure, we need resources. So one of the, you can't carry everything from the planet and go there, and moon has resources. So one of the questions we asked is, how can we detect metal resources on the moon? Now, there's no real signature for metal, but if you combine all the lunar data that we have, that gives us thermal, spectral, magnetic field, you create a stack of data. What you pull out are anomaly detection maps, which kind of shows. So what is a characteristic of metal? When you sit in a car and you go, it's sitting in the sun and you go touch the seatbelt metal, it's hot. So metal gets heated very quickly. That's a signature that it gives a particular kind of IR emission. So when you put all these maps together and you see, what you can pull out of this is like being a detective scientist. You can pull all kinds of amazing information. This was a sample of that. We looked at this crater created, basically, utilized all the different missions and created a synthetic map. These are basically blue is cool or smooth or different characteristics. And then ultimately you generate, a heat map or an anomaly detection map. So all I want to tell you is There is so much open, so many ways to ask questions, so many interdisciplinary important questions. That's what I would like for you to take away from this talk. And ultimately, I think interdisciplinarity as a word is really key. Data scientists don't know the pitfalls, and domain scientists don't know the full toolbox that exists in AI. And that partnership is critical. Without that, we will go into different directions and will not be able to achieve the full potential of this tool. And so this is the basic formula for NASA Frontier Development Lab, research talent, young people, postdocs, challenge plus data, bringing the data, creating database, uniform data, and of course, capital plus capacity, working with the private sector, the public sector, to create the funding mechanism so you can address these topics. And I think what the Frontier Development Lab, as at least, has taught me, that even with really small investment, you can do breakthrough science and you can demonstrate what that capability is. And I really thank you for being a quiet audience so far. I hope you'll have questions and giving me an opportunity actually to speak at the first colloquium post-COVID. Thank you so much.
So thanks a lot, Lisa, for a very wonderful talk. This could actually turn an AI skeptic to a believer. So would you be okay to take some
Sure.
No, I get loud enough. Don't worry about that.
No, because there are people on the Zoom.
This is about your point of prediction of space weather using the AI/ML technique, sun-induced disturbances in the near Earth environment. As you know, well, being an expert in the field, you know that during the solar maximum phase, we get 7 to 8 CMEs per day. And during the solar minimum phase, we get 1 or 2 CMEs per day. And not all these CMEs give rise to geomagnetic disturbances or the type of satellite loss or the odd numbers with the reason a deep CME. And these CMEs, they come with a wide variety of speeds, and the fastest one can reach the near Earth space in about 15 or 16 hours time as per the available prediction models. So given this large amount of data dating back to 1970s, ever since OSO was launched, and 50 years of data, and given the sufficient amount of lead time that is available, 15 hours, how do you think the AI and ML techniques can be effective in predicting the occurrence of the geomagnetic storm or the DST going to less than minus 100 days?
Where do you want me to begin? I just began on the 5 years. I mean, we are doing our AI/ML strategy, all that. I think we have demonstrated a proof of concept, and I think we have to globalize it. I think we need resources, basically, to kind of ask those questions, figure out what data. You have to render the data into AI/ML format. That takes resources and time. And then basically work with the private sector to utilize the tools they have, the inference models they have developed, the optimization scheme they have developed. I don't see any other way, no matter what the community tells. I think what I have seen possible in this small venture is the way we have to go. We have to engage a broader swath of domain experts, computer experts, private sector with their tools, with their compute capability. We don't even have fast enough GPU to run the experiments. But there are visions. I'm writing the Heliophysics AI/ML strategy. I've done that. Yes, we have vision. short-term, medium-term, 5-year vision, as I was talking of, how you can create space with a constellation with many of these concepts. You can create a concept of predicting BZ and then create a constellation to predict that. That's so your question about how CMEs behave. I mean, the fundamental aspect is the orientation of the magnetic field, whether solar wind is going to get connected and get energized inside the geospace environment, or it's just going to go around us. That is, and we don't know how to predict that till we measure it at is only half of.
So can I take your answer as how do you predict the southward component of BZ is the key, right?
That's a very important component. And how? Well, I mean, scientists have been trying for a long time. It is like the DEM measure I showed, differential emission measure. Scientists have used that forever to really do what AIML did in terms of predicting spectral irradiance variability for one of the sensors, which is actually better than the DEM. But the thing is, you can go back and say, why is it better? So you can learn from it. So these are examples. So for BZ, I think we don't have enough data for scientists to actually, the way they have tackled the problem, to even get to that closure. I mean, I've supported many topics over the years. But I think AIML would be a fascinating approach. Aditya is launching, it adds another component to the L1 environment where you can actually begin to look at the structure of the solar wind with multiple satellites like we are doing with Magnetospheric Multiscale. So now we would have Aditya L1, we have wind, we have ACE, we have SOHO, we have what is the NOAA satellite name I'm forgetting. We can begin to utilize all the data we are taking to ask these important questions.
So that's precisely the point. So for example, we have SOHO since 97 or so, and ACE is there for at least now more than a decade, which gives right information about what's happening with the planetary components and all. But still, what is missing as far as the prediction of BZ is concerned, in your opinion?
I think we cannot answer the physics question, right? I mean, we are looking at 93 million miles between what is launched from the sun and what arrives at L1. So there could be a really clever theoretician or a group like Piali's who will come up with a very clever theoretical intuitive idea. That hasn't happened yet. Barring that, we have to kind of take traditional approach we have of all the physics and models. That's what we are doing.
Okay.
And there isn't enough data in between, right? In this 93 million miles, it's like two boundary conditions.
The question that I'm putting in
I'm glad that there are some volunteers to pass on the mic. Yeah. Thanks. So the question is regarding collecting the data, right? Virtual observatory, I mean, for stellar physics and other galaxy thing, that brought a lot of data in a particular format, so that you could actually interoperability and you can dig through various data from various missions or telescopes, etc. So in this case, in heliospheric physics also you have data. I mean, here also when you have a planetary mission, you have a mission to study the sun, etc. May be producing data in different varieties and different types of formats, etc. So from your point of view, in putting you have a question, and then as you rightly said, you need to have a collection of data which people can look into it, and you have tools and techniques which could be developed, or existing one which needs to be modified, etc. to do it, right? So one of the important components is to bring the data on a common platform so that you can look through it. So how difficult is that challenge to work in the US? I mean, each component, so I'm just looking at that component of bringing data on one platform. And the second aspect of it is in a country like India, what is the challenge? I mean, what's a different kind of challenge we have? Is there any difference, or the challenge we are looking at is similar across these two nations?
Yeah, these are very important questions. The straightforward answer would be this aspect of the challenge is very resource hungry, human resources and dollars, right? Because you're bringing all kinds of data. So I think heliophysics, at least in the US, through NASA, I would say, has always been very innovative in the way it created the data structure and made it available to community. I mean, SDO is a brilliant example of that, that serves as the data node for the rest of the world. But if you take an example from earth science, they spend a lot more resources for something like that. But our community just didn't have the resources, the budget. So they started using clever way of kind of bringing the data to community. I mean, those are details, but that's kind of one thing I think each group within their means have to look. The other thing I would say is that data has to be made available and accessible. They don't have to be AI ready. So rendering the data AI ready is a lot of cost and work. I would like to see that the community first kind of create a list of topics that is not answerable any other way, and then look for what data we would need to answer those questions, and then start selecting those data and render them into AI/ML. So kind of, if you try to grab everything, that's kind of often the tendency is that we want to convert, okay, this is important, therefore we're going to convert everything. It's just like what the ground-based observatory used to be, right? Everybody, so we calibrate the data. Well, who's going to use it for what? So I think we should be asking those questions up front. Take piece by piece approach. At least that's what I would say. I'm not saying that that's the NASA approach. When I think about the problem, that's how I do it.
It's also easy to actually, then you can show outputs.
Exactly.
That, right?
Exactly.
Rather, you just be transferring and without actually reviewing.
Yes.
So I have a very naive question. Like most of these interdisciplinary aspects are related to our planet or maybe to our solar system. But what about people who are working in like suppose black holes or AGNs? So what is your advice? Like how do they look towards these interdisciplinary aspects? So what should they look for?
There is no, so I can't, oh, you're there. I was looking, where is the microphone? I don't think that I gave you examples through the lens of heliophysics. As I was showing, we have tackled tackled topics in astrophysics, in astrobiology, planetary science. So there is no difference. It's the formula is the same. I mean, if you look at the last chart, it's the same formula. You have to ask the right question, bring the right data. If it is physics-based, you have to bring the right physics-based models. You have to bring the subject matter experts, all of that. And then the magic happens. I promise. There is something very transformative about this. When you see at the end of 8 weeks what these early career people produce.
Jayant has, I think.
Yeah. So there's a question online by Ravinder. So you can ask the question.
Hello. Am I audible?
Not very clear.
Not very clear.
Okay, so then let me just put this question on the chat window. Go while you will wait from someone else.
We'll take other questions.
Private companies are concerned only but they are affected. Now that they are affected with Elon Musk using many of his Starlink, One,
That's too much information to give.
because that's the problem in India also.
I don't think that it's a problem. No.
What? 7 years ago, Yuri Milner came here and called all the private companies to do exoplanet and ET and all those things. And everybody showed interest, but none of them came forward.
So
So
it's a two-way process. I mean, India has to engage itself with the international community. It's not somebody coming and preaching to you, right? You're doing your own science, and it has to be collaborative between the two groups, kind of you're providing data that allows someone to learn from it, right?
That's the question, that unless and until they see profit or they are affected, their business is affected, they usually never bother for it, unlike some other people.
You are absolutely right that the private sector world is not so much philanthropic, right? They operate on a return on investment. I have to share kind of a joke. When I went to the Silicon Valley, this is the first time, so my boss at Silicon Valley, he's the director of exploration directorate, and when I'm showing him, what I'm doing, he's asking me, well, tell me, what is the ROI on this? Now, I worked at NASA headquarters in the Science Mission Directorate, as I was saying, for 22 years, and I never heard that word. I absolutely had no idea what is ROI. I said, we are scientists, right? So what is ROI? So, how do I pay the people? What is the return on? I give you 200K. What is the return on investment? So that's the question you're asking. Very true. What I was demonstrating here is that keep an eye towards that. What you're developing has real life application. So science with relevance become very important. Very important. That doesn't mean you should stop doing only discovery science or black holes. But when you do that, you come up with tools, techniques that you're going to apply somewhere else. So kind of keeping yourself aloof from asking those questions is not good. So you have to figure out and demonstrate how you might be saving cost, mission cost or payload cost, or predicted capability cost, just any number of them. You have to spend time thinking about it while you pursue what you're doing. And you have to tell the private sector how they benefit. So it becomes, if you want their resources, it becomes your job to kind of demonstrate that.
And then take the question.
And I want to kind of, he's asking a very important question because it can be frustrating. Because it's no different anywhere, but we have succeeded. We have actually received a lot of support from Google.
That's what my question, because I am one of the signatory of Breakthrough Initiative, which was appreciated $100 million by that. But the subject, it matters on the subject. It was ET, it was exoplanet, a lot of people will come. But when it comes to space, unless and until your satellites are getting destroyed, nobody.
That is very true. That is so. What do you think I'm doing? I'm proselytizing. So there are different ways of doing it. I mean, like this, like that. We can like it or we can like it a lot.
So my question is related to what I'm asked. So the main challenge in this machine learning or AI-based algorithms is that it requires a lot of computing power. Most often you require GPU processors, a lot of RAM, big data storage. So the question is are you also thinking of some platforms, online platforms, where this rich data set can be hosted and then we can actually develop these algorithms and run there? Basically a platform which offers a lot of computing power. That has been the main bottleneck.
Very good question, and very much so, as I said, So SMD, Science Mission Directorate, is developing its own sort of AI/ML approach. Each division is looking at it from their own vantage point. And in my division, in Heliophysics, I'm kind of leading that effort. But there is, I keep data infrastructure separate from that, because that's something we need. That's not something what scientists need to do, basically. So this ML data that we have created through FDL. We are making it available through spaceml.org. That's what I was saying. I think you solar physicists must actually go to that website, download the data, see what the issues are, what the bugs are, and then you can write to the people who are kind of curating and managing. In general, NASA Goddard is going to be taking the lead on creating kind of platform-based approach, which is the right cloud vendor. If you haven't tried and tested, everybody sells everything, right? So you have to give community time to understand what is important. So there's a lot of stuff going on like that. We have to understand our needs for what would be most suitable. But that dialogue is ongoing and work is proceeding.
The Gaia network provides a platform for staging the data and doing analysis and even places have. Yeah. So they have each mission has its own place where you can't download the entire thing. You are processing there and only the result you download.
Yeah, we all our basic data is completely available. Or now we are talking about specialized data.
I'm saying that this space analysis also
is done there. Yeah.
So Jayan, and we just did, is it okay? So we have 3 more and
Sure.
Yeah. So question from Ravindra Banyan. So thank you for your interesting talk. Sorry for my question is slightly on different note. As you might know, the Yuval Noah Harari, the famous Israeli historian, is very vocal critic of the AI. In fact, he has described the AI as eminent threat to humanity comparable to global warming. Do you share his skepticism when it comes to the broader implication of AI to society? So it's much broader question, not just the science, but AI to the implication to the society.
I will answer this again, not from a NASA vantage point, but my own personal view. Einstein's E equal to mc squared was just knowledge, unbelievable knowledge. You can take knowledge like that and destroy humanity, or you can solve the power problem of humanity. It is up to us.
Very nice discussion. I have 2 quick questions.
I
have 2 quick questions. One is that you have showed the data degradation while time goes, okay, due to detector degradation. So is that implemented on AI data, which is available right now?
So as I was saying, we haven't taken any of these and operationalized them, but we want to.
Okay, and one more thing is that because there are a lot of AI predictions are going on, as we showed here in many of the slides, but we have not shown something about the plain or CME prediction using the magnetic observation data.
Sorry, I missed the last question.
Plain CME prediction using the magnetic field observations.
Plain CME prediction.
Oh, we have actually, that was one of our course topics. One of the difficulties with that we learned. That's why you have to kind of test these questions. Not all questions are answerable. So again, bear in mind that one view graph that I showed, where the blue line keeps on moving with the deep learning and the red line gets plateaued, right? More data makes more accurate prediction of whatever kind it might be, whether for scientific discovery or for whatever you're trying to predict. So in the case of solar flare, we could do the C flare pretty easily. That was pretty robust. But when it comes to X flares, which is the really deeper one, our data is very limited. So therefore, you really don't get good answers. Now, how do you solve that? All of a sudden, you just can't create more data from the past. Maybe in future, you can imagine putting more observatories to collect data. What do you do in the meantime? So the super resolution of magnetic field that I showed, you ask questions in different ways. And I really go back to, I really found your paper fascinating, right? You kind of tackled it completely orthogonally or in a different multivariate space, basically, right? You have to ask those kind of questions to figure out what are some of the observations that can lead to a different kind of answer, which will lead to your layered answer. So we have to be innovative and clever as scientists.
Hello, thanks for this wonderful talk. Thanks for this wonderful talk. I had a question like, you mentioned about data and all. So, is there any way that students can participate in handling those data? Like if NASA is doing anything using online platforms like Google Colab or Kaggle competitions, whether the data can be used efficiently and many people can participate in the.
I should put you in touch with many of the Indian students who are doing that. So this is very much the case. Frontier Development Lab, even during the hybrid mode, you can imagine the time difference, right? There were Indian students participating in topics. So this is available to all. You have to compete, and then participate. But this ML, space ML data that I was talking of now, because we have created kind of quite a collection of it, we have put it out for the community to use.
There's one last question, so he was very keen to ask. So
Sure.
I'm sorry.
Okay. First of all, it was a wonderful talk. So in one of the slides, you showed that NASA downloads 2 GB data in 15 seconds. Okay,
And
so,
that's still dated information.
okay, so that data is ML processed data or it's okay, it's just the raw data.
Yes, exactly.
So why can't we just incorporate ML in the satellites and then use the data so that
Well, that is the future. It's a very good question. That's what you kids are going to do for future missions.
yeah, okay, because now we will be confident with the accuracy because we are using it for a long time.
You're spot on.
Thank you.
Okay, so now that because of the paucity of time, let's put an end to the Q&A now. Thank you, Lika, for patiently answering all the questions and also for a wonderful talk. But before we end, a small memento from IIA. So I request Professor Anatoli Subramanian to have This is a picture taken by our engineer, Anchit Dorji, who may have also been to Hanley. So, yeah, this picture taken by him.
That's beautiful. Hey, and two
So we'll take this
women
picture and
holding
put it on
this.
social media. We'll tag you. Anchit will be very happy.
Thank you so much. Thank you. Yes, because I cannot take it from here. I have to pay for extra luggage.
So you let us know your address in India.
Yeah, it will write.
Right? So I'll take the address. Okay.
Thank you so much. It was a pleasure.
Yeah, thanks a lot everyone for joining us and for watching this session. Thank you, Lika, once again.